11.2 Systems of Linear Equations. So let's look at systems again, and let's see if we can solve them a different way. So I'm going to end up using matrices, so we need to figure out what a matrix is. So this system, x plus 4y equals 14, 3x minus 2y equals 0, that can be represented with this matrix. It's actually called an augmented matrix. And the reason it's a matrix is because it's a rectangular array. An array is just an arrangement of numbers. Okay, and things that are moved like in this direction, it's called a row. In that direction, it's called a column. So this one has 2 rows and 3 columns. Let's practice writing those. So write the augmented matrix. So this system could be written with this matrix. So 3, negative 2, and then that 3, negative 2, remember there's a 1 in front of the y, 1, negative 2, and make sure that we place a bar where the equal sign is, and then that works. If I look at this one, notice that this one has 3 variables, so every single one of these should basically be written with 3 variables. So we have 3 x's, we have negative 2y plus 0z, and then the 5 needs to move across to a negative 5. Okay, so this one would be negative 2x plus 0y plus 4z equals a negative 2. And that one's written correctly. So then the matrix looks like this. 3, negative 2, 0, and negative 5. Negative 2, 4, negative 2, 0, 4, and a negative 2. And then finally 1x, 4, negative 7, and 0. And make sure we show that there's an equal sign. Okay? Then we get to something we saw earlier in this chapter, and these are the rules we play by. And that just means that if we try to solve through matrices, so by using a matrix, we can still interchange rows, we can multiply, and we can add and subtract rows. And you'll see here what that means in just a second. So let's see what that looks like. Alright, apply the row operation. R2 equals 2R1 plus R2. So the capital R2 is the new second row. And the new second row can be found by doing 2 times R1, so 2 times 1 is 2, 6, and a negative 8. And then we're adding R2. And a negative 2, negative 5, and 3 is what R2 is. And then you add, so we get 0. 6 plus negative 5 is 1, negative 8 plus 3 is a negative 5. So that means my new matrix looks like this. 1, 3, negative 4, because we did not change R1. It says we have a new R2, so leave R1. And then the new R2 is 0, 1, negative 5. Right, and there's the equal sign. Let's look at what this really means. So this top line, these are your x's, right? So we have 1x, and 3y equals a negative 4. And then here we have 0x, which usually we wouldn't write, and then plus y is equal to a negative 5. So that means y is a negative 5. Well, then we could solve this by doing x plus a negative 15. 3 times a negative 5 is a negative 4. So you would get x equals plus 15 equals 11. So that system has a solution. It's 11, negative 5. Alright. We'll continue with that process a little bit. So let's say we have 1, 3, negative 4, 0, 1, negative 5, right? Find a row operation that will result in the augmented matrix having a 0 in row 1, so row 1, and in column 2. So now we want a 0 over here. So if I want a 0 over there, then let's see, if I multiply the bottom one by 3, so if I do 3 times R2, and then if I take that and subtract it from R1, right? So now I need to make sure I write things correctly. So we're going to do this bottom one times 3 and then subtract it from R1. So the new R1 is going to be the old R1 minus 3 times R2. Okay, so it's 1, 3, negative 4. And then we're going to do 3 times R2, which is 0, 3, and negative 15, and then we're going to subtract, right? So we're going to do 1 minus 0, which is 1, 3 minus 3, which is 0, and a negative 4 minus a negative 15 is 11. And you see you get that same sort of answer, because now we could do this. So we didn't change the second one. So we already knew from the previous example we got y is a negative 5. And then on this one you get 1x plus 0y equals 11. And you get that same answer that I showed you a moment ago, right? So again we get 11, negative 5 as an answer. So what that means is if you try to solve a system through a matrix, if you can get this bottom one here to say y equals a negative 5, then you can backtrack and solve for it, either sort of the old-fashioned way, so backtrack and solve, or you can continue and you just make sure you have a 1 here and 0 there and then the number, and then here is 0 and there are 1. Okay? And that has a special name. So I forgot to do the bar here. So that is row echelon form, and that means that you have an entry in row 1, column 1, which is a 1, and everything else below it is a 0. So I'll give you a couple other examples. So let's say I had a system with 3. So we're looking for something that looks like this. Let's say this is 2, 3, and a negative 1. So this is a system in 3 variables that has the answers x equals 2, y equals 3, and z equals a negative 1. Okay? This would be okay as well. So it says the first non-zero entry in each row after the first row is a 1. Zeros appear below it, and it appears to the right of the first non-zero entry in the row above. So that's sort of the pattern over here. So if you have a 1 here, then this needs to be 0 and 0 and 0. So there's a 0 below this one, and then you can get a 1 here and then the 0. It says any rows that contain all zeros to the left of the vertical bar, so any rows to the left of the vertical bar, so that means these, appear at the bottom. So this is also okay if I had something that looks like this. And then, let's say it said 2, 3, and 0. So I have a question for you, and I think you need to figure that out a little bit on your own, but you see it somewhat. Say, what does this mean? Alright, what does this mean? I mean, here you have a row that says 0x, 0y, 0z equals 0. So you get something like 0 equals 0. Okay. So let's look at this stuff and see if we can now go all the way through, and we'll just use matrices. So let's switch colors for the heck of it. Right, so what do we have? We have a 1, a 1, and a negative 1. No negative 1. We have 4, negative 3, 2, and 16. And we have 2, negative 2, negative 3, and 5. So that is the matrix form. So what are we going to do? Well, the idea is that this one is great, yeah? Now we want to get a 0 here, and we're going to get a 0 over there. So that's sort of the first job that I have, is how do I get that? So what I'm going to do is that I want a new R2, and my new R2 is going to be a negative 4 times R1. If I do negative 4 times 1, I get a negative 4, and then if I add it to R2, then that would be my new R2. Yeah? So let's see what that looks like. So the top one I'm just going to copy. I'm going to leave it as 1, 1, negative 1, and then a negative 1 over here. Okay, so this one is okay. We actually want to start with a 1 here, and we'll worry about the other stuff here a little bit later. So the new R2 is a negative 4 times R1, and then you add it. So a negative 4 plus 4 is 0. A negative 4 plus a negative 3 is a negative 7, and a negative 4 times a negative 1 is actually 4, and 4 plus 2 is 6. Okay, and then don't forget the last one, 4, or negative 4 times a negative 1, that's also 4, and 4 plus 16 is 20. So there is my new R2. I also want a new R3. So R3, basically the same thing. I have a 1 there, so a negative 2 times 1 would create a 0 there. So a negative 2 times R1, and then I'm going to add that to R3. And it's custom to show what you do over here. Now you don't have to show every single step. So notice that I just immediately wrote down my answer. And the same thing over here. So a negative 2 plus 2 is 0. A negative 2 plus a negative 2 is a negative 4. And negative 2 times a negative 1 is 2. And 2 plus a negative 3 is a negative 1. And a negative 2 times this is 2. And 2 plus 5 is equal to 7. So now I have a new matrix that represents the same system. Okay. What I really want to get next is I would like to get another 0 over here. Okay, and at some point this needs to be a 1, but I want another 0 over here. So, and these two don't match very well. Now, you can do this in one step. Okay, so what I'm going to do is I'm going to take R2, I'm going to multiply it by 4. Yeah, and I'm going to take R3, I'm going to multiply it by a negative 7, and then I'm going to add that new R2. And hopefully you'll see what happens over here. Now, the top one doesn't change, right? So it's 1, 1, negative 1, and a negative 1. So my new R2 is actually just 4 times that. So, and you don't have to write this, but just for us, I think in this case it makes sense. So I'm literally just multiplying all of these by 4. So I get a new R2. So now I'm going to take R3, it's a negative 7 times R3, so it's a negative 7 times the old row, and then I'm adding it to R2. Now hopefully you can see why I did the multiplication here first. So 4 times a negative 7 is a negative 28, right? Okay, and the first spot is still 0, right? A negative 7 times a negative 4 is 28, and 28 plus a negative 28 is 0, and that's what I was really after. And then I do a negative 7 times a negative 1, and that is 7, and 7 plus 24, I need to make the new one, 7 plus 24 is 31. And then I do a negative 7 times R3, and negative 7 times this is a negative 49 plus 80, and a negative 49 plus 80 is actually 31 as well. And now that means that I actually have 31z is equal to 31. So I can divide all those by divide that by 1, right? So instead of having 31 equals 31 here, I can then just say, well, if I divide every part over there by 31, then I get my first answer. I would get 1 equals 1. Okay, now I said I don't need to write this. The reason I said that is because I really don't need a negative 28, 24, and 8 here because they all have 4 in common. So actually would have been better off if I had just kept that with smaller numbers, right? But I wrote these so that you sort of saw, hopefully you could follow along with what I was trying to accomplish. And so actually it's easier if I would have just left it as a negative 7 and then a 6 and a 20. So what I'm trying to tell you is I could have done all this sort of in once. So I could have done this here and written that, and instead of adding it to R2, I could have said, well, I'm going to add it to 4 times R2 and skip this one altogether. Okay? And what does that leave me here? Well, now I could keep trying to work this all the way through, right? Or if I now know that z is equal to 1, and I just like the backtracking at this point, I would just backtrack. So I get a negative 7x, sorry, keep thinking, these are my y's, so that's a negative 7y plus 6z, and that's just 6 is equal to 20, so a negative 7y is equal to 14, so y is equal to a negative 2. And then I have the last one, and that says, so this row over here says that I have x plus y minus z is equal to a negative 1, so let's just fill in what I have. X minus 2 minus 6 is equal to a negative 1. No. when I talk I make mistakes. Z is actually just 1, right? Is equal to a negative 1, so x minus 3 is equal to a negative 1 at 3, so x is equal to 2. So my final answer here would be the ordered triple, 2, negative 2, and 1. And then that is the solution. And this is solving it through a matrix, which is basically the same thing we did earlier, except you don't have to keep writing all these x's and y's and all that. Alright, so let's do one more of those. Hopefully you're getting the hang of this a little bit. So we're going to start by writing this in its augmented matrix form. So 1, negative 3, 2, and 6. Make sure these are all x. So yes, all the parts are represented. And then a 10, and 1, and then negative 8, and then 3, and then 28. Okay, so let's see what happens. I have a 1 here, which is great. I want a 0 here. So what do I want my new R2? Well, if I take 2 times R1 and I add it to R2, I should get a 0, right? So 1, negative 3, 2, and 6 does not change. So 2 plus a negative 2 is 0. And negative 6 plus 1 is a negative 5. And 2 times 2 is 4, plus a negative 3 is equal to 1. And 12 plus 12 plus 10 is equal to 22. Alright, hopefully I did that right. And then I want a new third row, and I want a 0 here as well, and that just means I can take R1 minus R3. So that's what I'm going to do. I'm going to take R1 and subtract R3. So 1 minus 1 is 0. Negative 3 minus a negative 8 is actually 5, right? And 2 minus 3 is a negative 1, and 6 minus 28 is a negative 22. Great. These are going to cancel, so I want a new R3 because I want to cancel the next 0 here, so I'm going to have 0 and a number, and then 0, 0, and then a number. So the new R3 is just going to be R2 plus R3. So what do we get? We get 1, negative 3, 2, and 6. I'm going to copy this one as well. And then the new R3 is 0 plus 0, or 0 minus, yeah, plus 0 plus 0, negative 5 plus 5, 1 plus a negative 1, and 22 plus a negative 22. And there's that 0, 0, 0, 0 that I mentioned over here. So that actually means 0 equals 0. So that we have infinite solutions. Okay, when you have infinite solutions, it is custom to write it in a format that expresses your solutions as sort of in terms of a formula or in terms of an equation. What I mean with that is the following. So this one we're done with. So this means I have a negative 5y plus z equals 22. Okay? And the top one says I have x minus 3y plus 2z is equal to 6. Over here, I can rewrite that one a little bit, and I could say that means that z is equal to 22 plus 5y. You guys okay with that? Alright, so I just moved that over, so I'm going to replace this z here with 22 plus 5y. So I'm going to get x minus 3y plus 2 times this thing. So 2 times 5y is 10y, and 2 times 22 is 44. And that means I get x plus 7y is equal to 6 minus 44 is a negative 38. And then I'm going to write that one in this x equals. So x is a negative 7y minus 38. And here I have z equals. So my final answer is going to look like this thing. So the solution to this system is going to be x equals negative 7y minus 38. And z is equal to 5y plus 22. And then this would be a good way to represent that that system. Okay, it allows you to quickly find your x and your z if you give me your y. And I believe that's it. Thank you.